We are going to look at direct proportionality as it is mentioned in differential equations. If you want to print the sheet that I'm going to use for like fill in the blank notes, you can go to this bit.ly link right here, diffeq_prop, watch the capitalization, and let's move on. So a quick algebra review. You should have learned many years ago that if two things are directly proportional, so if x is directly proportional to y, or if they said y is directly proportional to x, then y is a constant multiple of x. Y equals kx is how that is interpreted to translated to an equation, and k is the constant of proportionality. So let's look at it how it might be mentioned in calculus. So we have a situation here. It's exponential growth and decay. So P is the population of gnomes on an island. And then I tell you that the population grows at a rate directly proportional to the population size. And that is the key sentence that we need to interpret. The population grows at a rate directly proportional to the population size, and P is the population size. So when it says the population grows at a rate, this part right here, population grows at a rate, they're talking about the derivative of population, which you could write as P prime of T. However, in the world of differential equations, we often use the Leibniz notation, dp dt. And so dp dt is directly proportional to the population size. There's that statement, directly proportional. That means dp dt, if dp dt is directly proportional, that means it is a constant multiple of the population size, and the population size is P of T. Now, you can write P of T if you want, but I'm just going to write P. It is understood and it is defined here that P is indeed a function of T. So dp dt is a constant times P. And if we look at this situation, we have a differential equation now. I'm going to solve this through separation of variables. And this time it's P and T. It's not a Y and an X, but P is my dependent variable. I need to divide by that P. And so as I separate, dP divided by P would equal, and I'm going to move the dt over, so K dt. And now I need to find the antiderivatives of both sides. Left side, top is the derivative of the bottom, so we will have the natural log of P, absolute value P, equals, and be careful with K, because some people want to say the antiderivative is K squared over 2, but remember K is a constant. It is not a variable, so it's KT would be the antiderivative over here. So KT plus C. Remember, K is a constant. The antiderivative of 4 would be 4T, so the antiderivative of K is KT. And then I'm going to solve for P. We do not have an initial condition to solve for the C, so we're just going to get a generic equation. So I'm going to solve for P. And when I do that, I get the natural e to the natural log of P is just P. And now technically it should be absolute P. However, we are talking about a population of beings. And in that case, P would be positive anyway. We don't have a negative amount of anything if we're physically counting stuff. So P is equal to e to the kt plus c. However, e to the kt plus c, that plus c can be written as a coefficient of e to the kt. And if you look at that formula, it hopefully looks very familiar, because in pre-cal and algebra 2, when you dealt with exponential growth and decay, you learned a formula that looks an awful lot like that. P is AE to the KT. It may have been A equals PE to the KT. It's PERT, your continuously compounded interest, comes from this. So here we see the calculus reason we have that formula. But it does turn out that if one thing is directly proportional to, or the rate of change is directly proportional to P, it gives you that nice PERT formula. And this is a pretty common setup in the world of differential equations, so much so that I would say you should memorize that if you have a situation, and here it says dy dt, and it's hard to see that's a t, but that is a t down here. If dy dt is k times y, and what you're looking for, you want to make sure that you are directly proportional to the dependent variable. That is a y. I'm going to highlight that with a different color. That is a y. When you are directly proportional to the dependent variable y, then the solution will always end up being that good old PERT formula, or AE to the KT, or whatever variation you want to use depending on your constants. And it's good to know that because it cuts down, if you have to solve the differential equation, it cuts down on all these steps right here. And it's not saving a whole lot of time, but if you can expedite the process, that's good. But do keep in mind that you only want to use memorized shortcuts like that if it's a multiple choice question. In the world of free response questions, and here I'm talking about AP calculus specifically, if you're on the AP exam and it's a free response question, you have to show the individual steps that you used in generating these solutions. So only use these memorized approaches for multiple choice questions. And let's look at a few examples. I have two multiple choice questions and then two free response questions. The first one from 1985, dy dt is negative 2y. So I'm going to go ahead and write that down. Dy dt is negative 2y. And I immediately recognize that it is a constant multiple times the dependent variable. So dy dt is directly proportional to y. And in that case, I can immediately jump to the solution and skip the separation. I know that y is ultimately going to be some number times e to the k times t. In this case, k is 2 or negative 2. So negative 2t. And I have my solution already. So we sped up the process a lot. They give me an initial condition right here. Y is 1 when t is 0. So I could plug that point in. If I plug in 0, 1, we get 1 is equal to a e to the 0. Well, e to the 0 is 1, so 1 is just a. So then I can reset my solution. I now have a more complete solution. Y is equal to 1. I think I'll write the 1. E to the negative 2t. And then they ask, what is the value of t for which y is 1/2? So now I plug in 1/2 for y, which gives me 1/2 equals 1 e to the negative 2t. And we have to solve that for t. So we channel our algebra, and I'm going to go through this kind of quickly. I need to get rid of the exponential, so I'm going to take the natural log of both sides. So we have the natural log of 1/2 is equal to negative 2t, which then gives us, when we divide by negative 2, t is the natural log of 1/2 divided by negative 2. And I bet you that's not one of the options. And it is not. Now, there's definitely a natural log in here, so I don't like b or d. So let's see what they did. Natural log of 1/2 is the same thing as natural log of 2 to the negative 1 power, right? And then good old properties of logs. You have an exponent on your argument. Bring that exponent down front. Negative 1 times the natural log of 2 over, that was a mistake. Don't do stuff like that. Negative 2 over negative 2. Those negatives cancel, and it's natural log of 2 over 2. So I have warned my students many times, if you are doing multiple choice questions in preparation for the AP Calculus exam, be ready to use those properties of logs because they love to shoehorn those into the question. Let's go on to number 2. In a certain population, the bacteria increase at a rate proportional to the number present. So there is a verbal description of a differential equation. They did not define any variables or anything. So I think I'm going to let B of t, I'm going to let B equal the number of bacteria. When I choose my own variables, I kind of like to choose letters that match the situation. So B is the number of bacteria. And they say the bacteria increase at a rate proportional. So that means the derivative of the number of bacteria is proportional, is a constant times the number present, which is B. And you see right there, we have that exponential growth model in differential equation form. And I can very quickly write the population, the solution to this will be a e to the k t. Now we keep reading. And here's where it gets tricky. It says the number doubles in 3 hours. The number of bacteria doubles in 3 hours. Now, here's something, a little jog your memory here. With this exponential growth model, you may remember that A is the initial amount. And you could very quickly find that out if you plug in 0 for t to represent the beginning of time. E to the 0 would be 1, and so you'll be left with A, which will be the initial amount. And here they're telling me that 3 hours later, I will have twice that initial amount. So what they're saying is that the population at time 3 is going to be twice what I started with, which will be 2A. And then the question is asking, in how many hours will the number of bacteria triple? So the question is, when does the solution, B of t, equal 3 times the initial amount? There's our question. And so let's start piecing this together. So if B of 3 is 2A, I'm going to use that down here. So B of 3 would be A e to the k times 3, so 3k, is supposed to give me twice what I started with. And if you look at that, you can divide those a's out. Divide by a, divide by a. Those go away. And we have e to the 3k is equal to 2. And to solve that, you would take the natural log of both sides. 3k would equal the natural log of 2. And I find out that k is the natural log of 2 divided by 3. And I guess I could write the natural log step in here. I natural logged both sides here to get rid of the exponential. And now that's k, though. I didn't solve for the time when population triples. I found the constant k. So now I'll reset my solution. My solution is now b equals a e to the natural log of 2 over 3 times t. And the ultimate question, now I can finally get to the ultimate question. When is the population tripled? So when does b of t equal 3a? So when does my population model, which is that, when does that equal 3 times the initial amount? And again, kind of like when I solved this equation over here, you can divide the a's out. And this is an interesting problem. Move my head out of the way. And now that my a's are gone, I have e to the natural log of 2 over 3 times t is equal to just 3. We will again use a natural log to get rid of e to the stuff, which gives me the natural log of 2 all over 3 times t is equal to, that's a t, equal to the natural log of 3. And then finally, I am almost done. I will solve this by dividing by the natural log of 2 divided by 3, which is the same thing as multiplying by 3 over the natural log of 2. And so I have 3 natural log of 3 all divided by the natural log of 2 for my answer. And I hope that's there because I don't feel like doing those properties of logs. 3 natural log of 3 over natural log of 2. That is A. Good. They did not change it. They could have made that the natural log of 3 cubed in the numerator, but they did not. So there's that one. That was a tricky, but that was a lot of work. Okay. Two more, and I'm not going to finish solving these completely. I just want to read the prompt, and we're going to interpret the prompt and convert it to a differential equation that could be solved through separation. And these are first from some pretty old AP exam questions. And in 1983, they asked this question. This is the prompt. At time 0, a jogger is running with a velocity of 300 meters per minute. If I were working this problem out, I would go ahead and write down V of 0 is 300 meters per minute. Helps me think. The jogger is slowing down with a negative acceleration. So we're talking about the acceleration. Oh, here we go. Is directly proportional to time t. The acceleration is directly proportional to time t. A of t, acceleration, is directly proportional to time t. This brings the jogger to a stop in 10 minutes. And so that means that my velocity, if we're stopped in 10 minutes, that means my velocity at time 10 is 0. So we have two initial conditions. We have an expression for acceleration. We could do the acceleration. The antiderivative of acceleration brings back to velocity. And then these two initial conditions would be used in some way through the other questions asked. This is just the prompt, and that's the information I can pull from the prompts to kind of get my bearing straight before I move on and answer the rest of the questions. And if you want to see the rest of the questions, you could just Google 1983 AP Calculus exam and it will show up. Let's go on to number 4. We'll set this one up. This one's from 1993, so a little bit more recent. P is the population of wolves at time t years. So we have P of t when t is greater than or equal to 0. The population P is increasing at a rate. Direction. How about directly? Okay, so P is increasing at a rate. So right there, they're talking about P prime, but in the world of differential equations, we'll call that dp dt is directly proportional, a constant times 800 minus P of t. 800 minus P, where the constant of proportionality. Okay, so here they define the constant of proportionality. I kind of default to K anyway, but if I happen to have used a different constant, I would need to change it to K just to be consistent with how they're defining things. And then I said I'm not going to solve this, and I'm not, but your first step in separation would be to divide by the 800 minus P. That would get the P's on one side, multiply by dt, and then you'll do the antiderivative of both sides. And keep in mind, this is not dpdt is k times p. This is a little bit uglier, so we can't use that memorized solution from exponential growth that you knew in Algebra 2 and pre-cal. So there's a little bit of a direct proportionality as it relates to differential equations, and hopefully that makes a little bit of sense to you.